recording is on.
Okay, very well. So we're
Mario, can you still hear me?
I lost Mario. Is anybody else
Oh,
able?
I see. We lost Mario.
Yeah. All right. Let me just make sure the recording is still on. So you're free to go ahead and get started, Justin.
Okay, perfect. Thank you, Josh. So yeah, today I'd like to give a mini brain dump on post-quantum. And yeah, feel free to interrupt anytime. This is meant to be more of a discussion and a Q&A. So just to set the scene, the way that I think about it is that there's the 3 layers of the Ethereum layer 1. There's the consensus layer, data layer, execution layer, and each have to be separately upgraded. So we have BLS that needs to be replaced at the consensus layer, KZG at the data layer, and ECDSA at the execution layer. And within the execution layer, I would say there's 2 sub-problems. Sub-problem number 1 is what do we do in the short and medium term? How do we give optionality to people who want to migrate as soon as possible to a post-quantum wallet? And then there's the end game, which is the longer term solution. And one of my core theses since a while ago is that for the end game, we're going to need protocol level support. And the reason is that if we were to just naively swap out signature schemes, for example, swapping out ECDSA with something which is post-quantum secure, we're going to hit a bandwidth bottleneck extremely quickly. It's just not sustainable, not scalable. And to give you the numbers, an ECDSA signature is 64 bytes, a public key is 32 bytes. Whereas if you move to NIST standardized post-quantum schemes, the smallest one, the most efficient one, is called Falcon. And if you configure it for the lowest security level, which is level 1, you're going to get 666 bytes, which is more than 10 times larger of a signature than ECDSA. And so really one of the big motivating research and development problem that we've been working on for a year and a half, maybe a bit more than that, has been signature aggregation. Like, how do we take many of these very big signatures and squish them together into a single proof? And we have the luxury of being able to do this in Ethereum because we're in a batch setting, right? We have a single block which has multiple transactions, and so it kind of makes sense to batch them because they're literally packaged as a batch. And we also have the luxury, at least at the execution layer, to have a block builder and to have zkVM stuff where you have a prover that's like reasonably powerful and can do the aggregation for you. So without the aggregation, again, I think it's a non-starter because we would go from 25 TPS to something much closer to 3 TPS. And similarly for all of the other blockchains, if you take Bitcoin, which is currently at 3 TPS per second, 3 TPS, you would go down to something much lower, closer to 0.3 or 0.5 or that kind of ballpark. So the aggregation story starts at the consensus layer. And the reason why I looked at the consensus layer first was partly because I had this beam chain proposal, but also it's where we have the most amount of signatures floating around. So just to give you the numbers here, we have 1 million validators. They're each making an attestation once per epoch. There's 32 slots per epoch, so that's 32,000 validators or attesters per slot. A slot is 12 seconds, so you divide that by 12, 32,000 divided by 12, you get over 2,000 signatures per second. This is an insane amount of signatures that need to be processed, and there's certainly no way that we could do it without aggregation. We even have today aggregation with BLS. And so, how can we solve the consensus layer and basically hope that whatever technology we develop can be used at the execution layer and maybe also at other layers like the data layer. So one of the kind of starting points was, okay, what do we have in terms of options for aggregation? And long story short, there's only one option. The only option that we know of that is sufficiently flexible and efficient is to use SNOCs, specifically post-quantum SNOCs that could be hash-based or lattice-based. In practice, almost everyone nowadays uses hash-based SNOCs. There's a few kind of frontier research groups, including Microsoft and Jolt, that is looking into lattices. But primarily the industry has converged towards hashes, and I think hashes are really excellent because, at least for Ethereum, because they minimize the amount of security assumptions that you're making. You're just trusting a single hash function, and to a very large extent, blockchains already trust hash functions as a sunk cost. We use it everywhere in Merkle trees and in blocks and etc. So yeah, from a security standpoint and from a performance standpoint and a flexibility standpoint, we've gone down this path of aggregating signatures with hash-based NOCs. Now, one question you may ask is, what scheme could we use as the unaggregated signature? And here we have basically two classes of signatures that are most trusted. So there's actually the same families that we have at the SNOC. There's the hash-based SNOCs and the lattice-based SNOCs. NIST has standardized two lattice-based SNOCs. There's Falcon and the Lithium. The Lithium is kind of more friendly to use, and it's easier to sign. It's kind of very nice to verify, and so that's the one that it's also simpler. So that's the one that NIST is kind of suggesting people use by default. But unfortunately, it is quite large. It's, I believe, around 3 kilobytes. And also, it just so happens that it's completely unfriendly to aggregation. It's like one of the worst options that you can think of. And so in our context, that's kind of out of the question. Then you can go through the list. There's another hash function called Falcon. Signature scheme called Falcon. And here there has been some research in trying to aggregate it, but unfortunately, for various technical reasons, it's just very, very painful to work with. And especially if you want to be NIST compliant, you want to be using the NIST compliant hash functions, and so that doesn't seem like a good place to be either. And then that brings us to the hash-based schemes, which traditionally NIST kind of have put out there for diversity reasons and kind of as a backup for in case maybe lattices break or whatever. But this is not the default suggestion because the signatures are quite a bit larger. And so one of the key observations that we made is that for us, if we're going to aggregate the signatures, the size of an individual signature doesn't really matter so much because it will only be gossiped and shared off-chain, and in the context of the execution layer, only in the mempool, and then you only have the final aggregated SNOC that goes on chain. So in some sense, the main downside of hash-based signatures goes away once you have this aggregation, and that really makes the hash-based signatures shine. So in Lean Ethereum right now, we're making a massive bet. We're going all in on hash-based signatures, both for the leaf signatures that are unaggregated, as well as the SNOC that will go aggregate them. Now, if you zoom into the family of hash-based signatures, there's basically two options. There's what's called stateless signatures, which are the signatures that we all know and love, something like ECDSA or BLS, and those tend to be slightly bigger. So, on the order of a few kilobytes, think maybe 10 kilobytes. And then there's this other thing called XMSS, which is a stateful scheme. And here you have, roughly speaking, a 10x improvement in performance. So the signature is about 10 times smaller. They're only about 1 kilobyte. And the amount of hashing you have to do to verify a signature is also about 10 times smaller. So, about 200 hashes instead of 2,000 hashes. And the question you might ask is, okay, why isn't everyone using these stateful signatures? And the reason is that they're kind of dangerous, at least for end users that are unsophisticated. And the reason is that they have this security property, which is that every time you sign, there's an associated counter, like a nonce, if you will. And this counter should never be used twice. And if you do sign two messages with the same counter, then you're screwed. You basically leak your private key, and then anyone can empty your account. So the reason why these stateful signatures are especially attractive at the consensus layer is that this is actually a setting that we're very, very comfortable with. When you set the counter to be the slot number, validators today are not meant to be signing two messages with the same slot number, because otherwise they get slashed. And so there's a very, very big disincentive to get slashed. And there's a whole suite of tooling to prevent slashing. So, for example, in software, you have these things called anti-slashing databases, which record basically the messages that you've signed, and will make sure that you'll never sign two messages with the same slot number. There's also, defense in depth for some of the more sophisticated stakers that will have, some sort of HSM or hardware wallet to do the signing. And so that is, one of the key optimizations that we have to make the signature stateful. And one of the recent outcomes from literally last week, I guess, is that we managed to get the size of these signatures with 128 bits of security under 1 MTU. So an MTU stands for maximum transmission unit, and it's the size of the Ethernet packet. Like it's this the maximum size that you can send in one Ethernet packet without it kind of being broken down into multiple Ethernet packets. So if you want to have a super optimized gossip mechanism for your leaf signatures, then being able to fit the whole signature within a single packet is really cool, and unlocks UDP based communication and stuff like that. In any case, so we got the signatures under the MTU. So for IPv6, which has these bigger headers, the MTU is 1,280 bytes, and we got it under 1,200. So there's a little bit of buffer to have metadata like the slot number and the validator ID, blah blah blah, in addition to the signature, and the whole thing fits within the MTU. And so that's on the leaf signature side of things. And really what we're trying to do from a performance standpoint at the aggregation layer is to aggregate 1,000 signatures per second on a laptop CPU. And this is something that we have achieved, basically. So we have this project called Lean VM. It's under the Lean Ethereum GitHub organization, and it's a minimal ZK VM that is hash-based, and that is specialized for verifying hash-based cryptography. And nowadays it's with all the optimizations that we've put in, it's capable of aggregating 1,000 signatures per second on a laptop CPU. And the reason why we're restricting ourselves to these laptop CPUs is basically for decentralization. So we're assuming that a small subset of the validators will be running on a laptop. Let's say 10% of the validators will be running on a laptop, and then those 10% of validators will have sufficient hardware to assist the aggregation altruistically. So this is very similar to what we have today, where the validators altruistically help with BLS aggregation. But instead of being nominated to be aggregators, as it is the case today, it will be permissionless. So literally anyone can become an aggregator. And this permissionlessness actually comes from one of the superpowers of LeanVM, which is that you can aggregate aggregates even if there's non-zero intersection. So what does that mean? It means that if you have signatures A, B, and C, you aggregate A and B into an aggregate 1, and then you aggregate B and C into aggregate 2. Well, you see these two aggregates have a non-disjoint intersection. They both share signature B, and BLS really doesn't like that. So you can't aggregate across aggregates when there's when there is a non-zero intersection. Whereas LeanVM doesn't care at all. Like you have a much powerful model for aggregation, and this allows us to have trustless aggregators that could just work independently without this kind of top-down coordination, if you will. So we're in this fantastic position from the perspective of aggregation. And the other key performance metric that we have for LeanVM is what we call 2-to-1 recursion. So if you have two aggregates and you want to build a meta-aggregate, you're basically doing SNARK recursion. And here we got the recursion time down to about 800 milliseconds. So we're not completely happy with that number. We want to get it down closer to 250 milliseconds. But yeah, this is ongoing work, and the person who's leading this is called Emil, and he's really doing a fantastic work. And we know from another project, there's this other project called Plonky3 Recursion that managed to get 250 milliseconds recursion time. So we know there's a proof of existence that it can be done, and we're relatively confident that we can get there as well. Now, when working with SNARKs, especially at the consensus layer, we want to make sure that there's literally zero bugs, because a soundness bug would be really, really bad, right? Because you'd be able to fake someone signing when they didn't sign, and then you can cause them to get slashed, and you can eject validators. You basically have a lot of control over consensus if you can fake these proofs, and it would be really, really bad for Ethereum if there was a bug in LeanVM. And so our strategy has been to make LeanVM as simple as possible. Hence the word lean. So lean not only refers to the lean cryptographic assumptions, just the hash function, but also the amount of code in order to implement it. And the design of LeanVM has 6 instructions, all of which are very natural. So you have 4 simple operations: addition, multiplication, a jump instruction, and a memory instruction. And then you have these 2 precompiles that are slightly more complicated. One is a hash, so it's the Poseidon hash in this case. And the other one is a field element extension, because you're not doing only mathematics on field elements, but you're also doing it on extension fields, which is these field extension elements are used in the recursion, which is why we have this precompile. But overall, we want to keep things extremely simple, and the whole description of the LeanVM verifier, which is the key cryptographic essence of it, is on the order of 1,000 lines of Python code. right? So like all of the hardcore cryptographic complexity is condensed in just 1,000 lines of code. And that is a fantastic outcome from a complexity standpoint. Now, one of the things that we want to do as well, in addition to keeping complexity low, is to end-to-end formally verify the whole thing. And here we're in a really fantastic position where formal verification has gone through an inflection point literally in the last few weeks. So in February, AIs were able to build formal proofs of theorems that were, on the order of 1,000 lines, and we actually had one of the theorems approved called the Polyshock-Spearman lemma in the context of these hash-based snarks. But then, last month in March, we had AIs automatically generate proofs that were hundreds of thousands of lines long, and that was in the context of the Fields Medal result from 2022, the optimal sphere packing in 24 dimensions. So this is like bleeding edge mathematics, and an AI over 5 days just produced this proof that was 500,000 lines of code, which is absolutely insane. And now we're seeing this formal verification framework called Lean 4. The word lean, is actually colliding with Lean Ethereum. These are two different things. There's Lean Ethereum and Lean 4. But actually, these two leans are very much symbiotic. At least Lean 4 is helping. It's going to help Lean Ethereum in a big way. So what previously would have taken many months of human effort and cost hundreds of thousands of dollars to do will be a job that will cost maybe tens of thousands of dollars and will be done in a matter of weeks, maybe possibly even days. So this is the situation at the consensus layer, and I just want to pause to ask for you guys to ask questions. One thing. Okay, go ahead. Yeah, I'll just pause here.
Thanks so much, Justin. I think somebody just unblocked the mic by mistake there, but awesome. Thank you very much. Again, I'm sorry about my internet a moment ago.
No worries.
Folks, if you have any question, please raise your hand. Feel free to ask, or feel free to write in the chat as well if you cannot use your mic. But yeah, feel free to take the opportunity. And Lee has a question. Go ahead.
Hi, Justin.
Hey.
Yeah, happy to see you again, and thanks for the explanation. I'm happy to hear that the progress of formal verification. I'm just wondering, like you mentioned, that there already some parts has been done, so I'm wondering
Yes.
which part is done.
Yeah, great question. So when you're dealing with a proof system, roughly speaking, there's like 3 layers. Actually, in our case, 4 layers. So what are these 4 layers? At the very bottom, you have the mathematical foundations. So here you have, in the case of hash-based signatures, you have the so-called proximity gaps theorems that we rely on. This is basically very sophisticated linear algebra. And here I mentioned the Polyshock-Spearman lemma, which is part of proving that the mathematics is correct. And the Ethereum Foundation has invested a lot in a library called ArcLib. So Arc is the Arc in Snark. It stands for Arguments of Knowledge, and Lib is library. So it's a library to prove that arguments of knowledge are sound. It's written in Lean 4, and we basically have a proof of soundness that Fry, for example, is correct, and like Spartan is correct, and Were is correct. So you have these building blocks that we can now prove are sound, meaning that they have provably 128 bits of security in a cryptographic sense. So that's good. That's the basic foundation, and then level 2 is the end-to-end proof system. So here, basically, you take all of the components together, and you have what's called an IOP, an interactive oracle proof where you have, for example, a memory argument. This could be something like logup, and you have your PCS, which might be where, and then you have some like subroutines like sum check or whatever it is, and you kind of stitch everything together in a proof system. And here we've started making progress. I already mentioned Spartan, which is a proof system. We actually use Super Spartan in the context of Lean VM, or actually a variant of it. And what needs to be done basically is to formally specify the proof system, prove that it mathematically that it has the soundness that we want, and then prove that it's basically equivalent to the verifier in Python that I mentioned, or the verifier in the Lean ISA, because we're taking the Python and compiling it to the Lean ISA. Okay, so that's level 2. And then level 3 is the so-called arithmetization of the ISA. So in our case, we have this super trivial ISA. And one of the great news here is that we have done formal verification of ISAs in the context of RISC-V. So RISC-V is a much more complicated ISA than Lean ISA. It's about 10 times more complicated. It has 10 times more instructions, and each instruction is much more complicated as well. And the good news is that we have already formally verified the implementation of SP1 Hypercube and OpenVM, and then we're also working on formally verifying the correctness of the Pico arithmetization. So this is something that is very much under control because we've done it on much bigger systems. And then there's the final layer that needs to be formally verified, which is the Lean ISA program. So in our case, the program is going to be the aggregation program that takes multiple XMSS signatures and squishes them into one. And it's possible this is where like most of the effort will need to happen, but there's a very recent project called EVM ASM. So this is an implementation of the EVM in assembly, in RISC-V assembly specifically. It's by this guy called Yoichi, who's been in the space for over a decade. He took a hiatus, but he's back. And he's basically been using AI to not only generate the assembly, but also prove that it's correct. And basically, a similar approach will probably work for aggregation of XMSS signatures. And the EVM is much more complicated than XMSS aggregation. And so if Yoichi can do it for the EVM, certainly we can do it in our context. So long story short, we've been able to do the formal verification in a much more complicated setup, specifically for the ZK EVMs. And really what we need to do is reuse these techniques in the simpler Lean VM.
Thank you so much, Justin. Andres has a question. Oh, you're very loud, Andres. I think your mic. Andres, can you try to?
Yeah, we can't hear you. It's very distorted.
Yeah, sorry, man. Before we used to hear Andres well. Yeah. Yeah.
It's better now?
Yeah, it's perfect. Yeah, go ahead.
Thank you so much. So if I understood correctly your previous answer, you probably have already answered my question. But yeah, I was also watching a few days ago a call core devs had our layer 1 CK EVMs, and they were talking about this EVM ASM project where they were using Lean 4 for doing both the the opcodes of the EVM and also the proving of the opcodes. So my question was if the Lean4 was only being used in the EVM aspect of Ethereum, or if it was also used in Lean consensus. But I think that the answer is yes, because you were talking about doing the verification of the signature aggregation. So yeah, how my question is, how is in what ways are we using Lean4 to do some formal verification in the consensus layer?
Yeah. So for high assurance software like Ethereum, Lean4 is the perfect match. Oh, sorry. Thank you. It's really an amazing match. And we've been wanting to do end-to-end formal verification for a very long time, but now we actually reached a point where formal verification is so cheap that it's starting to eat the world. And various people have this saying, which is Lean4 is the new Rust, right? In a context where generating code is extremely cheap with AI, the bottleneck, the scarce resource is verification. And formal verification is the best type of verification that you can hope for, because it's automated. You don't have to read the proofs. You just have to read the theorem statement or the claim that you're trying to prove. And I actually think that it's not just Ethereum that's going to be using Lean4 everywhere. It's the whole world is going to be using Lean increasingly. Like right now, we've reached a point where AIs can prove one Erdos theorem per day, Erdos like open problem per day. So there's about 1,500 Erdos problems. Erdos is like this very prominent mathematician where he would just like create lots of open problems across his life. And just yesterday, there was this 60-year-old open problem which was solved by an AI, and there was like some genuinely like new mathematical insights that came from the AI. But the reason why I mentioned Erdos is because every time an Erdos problem is proved, the AI will generate the math paper like a PDF that is human readable, but it will also generate a Lean4 proof automatically. And so now, it's kind of taken for granted that if you're going to solve one of the Erdos problems, you have to provide an accompanying Lean4 proof. And I think the same thing's going to happen in other places. Lean4 was originally developed for mathematics, and so it makes sense that it dominates there. But more and more, it's being used to prove statements about code. So basically, in the zk-EVM context that you mentioned, EVM ASM, you have a description of the EVM, a formal specification. You have a description of RISC-V, also in Lean4. And then you have your assembly, and then your theorem is that the assembly is a faithful implementation of the EVM in RISC-V according to these specifications. And then you might have like other auxiliary theorems. For example, you could have that your RISC-V specification is equivalent to other specifications, potentially in other languages like ROC or K, which are formal specification languages for which we also have EVM specifications. But yeah, like we're entering a brave new world where everything will be verified. So not only will we, right now we're entering this weird phase where all of the bugs are being found, with things like Mythos. But not only will we have 0 bugs, but we will also have a proof that there's 0 bugs, which is the ultimate end game for verification.
Yeah, thank you so much. It is actually actually incredible to feel that now AI can prove that the answer that it did is correct. So yeah, I think what you're saying is something like really big. Thank you so much.
Yeah, and if you look at the rate of progress of AI, you can just draw some lines basically and extrapolate. And it's quite plausible that by 2028 we're going to have all of known mathematical knowledge be formally verified. There's maybe on the order of 1 billion lines of mathematical proofs out there, or maybe like 10 billion lines of proof. That's kind of an upper bound, and that's the kind of task that soon the AIs will just be able to gobble up and digest. I don't know if you've seen the documentary on the founder of DeepMind. It's called Thinking Game. It's about Demis Hassabis. There's this like famous scene where they were able to solve the protein folding problem using AI, and one of his colleagues says, how are we going to present this to the world? And originally they had this idea of an API endpoint where you submit your DNA sequence, and they would kind of give you the protein as a response. And then one of the engineers said, hey, we have about 300 million known proteins. Why don't we just why don't we just basically fold all of them? And that's what they did. They just took all of the known protein sequences known to humanity and just folded everything and provided that as a free resource. And we're going to do the same thing for all of known mathematics very, very shortly. And then eventually we'll do the same thing for all of code. So we're kind of as a humanity, we're kind of going through these checkpoints and milestones, and we're living in a brave new world where you're witnessing this on a month-by-month basis, which is crazy.
Yeah, I haven't seen that paper, but I will take a look. Thank you so much.
It feels very exponential, like thinking about how beacon chain formal verification before it was deployed was happening for like long time, and it was only partial. In the end, like wasn't as much useful based on how expensive it was to done. Like we are now on the completely different spectrum. It's incredible. Also for like DeFi security, it's very exciting, Justin. Like thank you so much for diving into that. But my favorite part is just the coincidence that like the Lean and the Lean 4 language is just get so useful now when we have Lean Ethereum. Like it's a great coincidence.
It's actually not a complete coincidence in the sense that the reason why Lean 4 is called Lean is because they follow the same principles as Lean Ethereum. They want maximum simplicity, and they want the so-called kernel, which is basically where you have all of your axioms, and you have the deduction from previous statements to new statements. So that's the core reasoning engine, if you will. And in Lean 4, the core reasoning engine is very, very small. And it's actually small enough that there's multiple implementations. So there's one in C++, I believe, one in Rust, and there's also a recursive one in Lean 4 itself. And when you work with these formal verification frameworks, you basically have this notion of a trusted code base, which is the kernel, if you will. And not only is the kernel very lean and small, but they've adopted the same strategy as Ethereum. So they've leaned on diversity to hedge against bugs in the kernel itself, which is a cool coincidence.
Yeah, of course. I mean, naturally, like best engineering principles and the approach that makes the protocol strong is like what benefits from it. So that's great to see. We have the similar approach there, right? Not just a coincidence. Cool. So we talked about the consensus before. Do we want to move further, or do you guys maybe have some more questions, something quickly to touch on? We are like almost off. Okay. We have a question, so let's do it quickly as well.
Hello, Justin. So I wanted to ask you the question that how will light clients will be with an environment of formal verified Ethereum?
Light clients. Okay, great. So the good news is that the best type of light client that you could hope for is snark based, and we're basically snarkifying all of Ethereum, and we're also formally verifying the snarkification. So really, what you'll just do is just verify these, one snark per slot, for example, and then that's basically job done, at least for the execution part of things. And then there's also data availability, where you have to do data availability sampling, and this is kind of the end game that Vitalik envisioned quite a while ago, where as a light client, you just verify a snark and you do a little bit of data sampling, and then you're done. Now, at the execution layer, we have ZK EVMs, and the direction that we're going in the short term is to have a diversity of ZK EVMs, something like 5 of them. The exact number hasn't been really settled. But the interesting thing here is that they would be enshrined, meaning that today as a validator, you have a choice as to which clients you run. In the future, there's kind of no choice, at least on the ZK VM part of things. So it's kind of dictated by the protocol, and you would have some sort of a threshold. So if 3 out of the 5, for example, agree, that's your source of truth as to what the canonical Ethereum is. And at the consensus layer, it would be a similar thing, but it would be non-enshrined. So at the consensus layer, there would still be optionality as to which clients you run. So you could run Prism or Lighthouse or whatever it is. And you can also choose your proof system. But eventually, over the very, very long term, what I expect might happen is that we're going to move towards something which I call canonicalization. So it's kind of a stronger form of enshrinement where there's only one that is picked. So once we have sufficient performance and we have end-to-end formal verification of the ZK EVMs, we can just pick one and call it a day. And we can probably do something similar at the consensus layer. So in the endgame, if you will, the true endgame final, you should just be verifying one proof, and it's kind of dictated by the protocol, and it's like provably secure, and that's the definition of Ethereum, and you're done.
Yeah, thank you, Justin. It's really great to have like a native light client, basically, like if everything is ZK, and it sort of just works compared to like the SPV approach or some like crazy light client protocols we tried for years. I mean, Andres has another question.
Yeah, so what you were saying is that in that case, we will have like only one client implementation, and we can formally verify that client implementation, and we will use that one.
So yes and no. The part that would be canonical and enshrined would be specifically the state transition function. So that is about 10% of a traditional code base of a full client. What a full client will do, in addition to verifying the state transition function, is do all sorts of ancillary things. So for example, it might maintain the mempool, it will maintain a database, maybe for the state. It will have a whole peer-to-peer networking stack, and it will maintain the fork choice rule, and then blah 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 blah. Like it will do all sorts of other ancillary stuff. And here, fundamentally, you can't really enshrine it. It's fundamentally off protocol, and here we would still have a diversity. It's just like the core consensus kernel, if you will, that would be enshrined and canonicalized. And I like the term Mario native light client. Is a pretty good term.
And yeah, I don't know if this is off topic, but it is impossible to formally verify a full client.
Yes and no. So the thing is that there's like all sorts of difficulties. So one of the difficulties as a when you're developing a client is that you don't know which environment you're running in. So for um, the state transition function, we can have a canonical ISA. So you could have, for example, RISC-V being the canonical ISA or lean ISA being the canonical ISA, and that's kind of fixed. And you can think of it as a virtual ISA, if you will. But when you're running on real hardware, there's like essentially unbounded diversity of hardware. There's like x86, there's ARM, and there's AVX, and there's all sorts of flavors of SIMD, and then if you're dealing with snarks as well, there's the whole like GPU proving aspect. So you have to work with CUDA and kind of capturing all of this complexity is very, very difficult to do. I mean, in principle, it is possible where every time a CPU vendor produces a CPU, they have a corresponding like lean-4 specification of how the CPU works, and then you somehow maybe when you download the software, you make sure that the ISA is kind of is compatible with the bytecode or something. But this is like very, very futuristic. It could potentially be done. The thing is that when you zoom out and you ask about diversity, traditionally the number one answer was security, and I think we'll be able to a large extent to move past that. But the other answer has been governance, and I think here it is healthy actually to specifically embrace the fact that there are some things that you can't easily formally verify, because as a second order effect, you kind of get a more robust social layer and governance that is harder to capture. And then there's a third aspect actually, which traditionally I have underrated, which is innovation. So what we've seen in the ZKVM context is that the innovations come from different teams. So there's, roughly speaking, 5 teams, or maybe a bit more, that innovate, meaning that they come up with these new ideas to make the ZKVMs faster. And the ZKVM teams all copy each other because it's all open source, and they all it kind of lifts all boats, and it's a beautiful thing to see. And this has led to basically 10x improvement per year for the last few years, which is mind blowing. And in the context of the ZKVM, we want to increase the gas limit by 400x. So we're at 2.5 megagas per second right now. We want to get to 1 gigagas per second. So that's a 400x. And in order to get this 400x, we're going to need a bunch of innovations. And so it's kind of strategically valuable to keep that diversity purely for innovation purposes, if not also for the benefits that we get from a security and a governance standpoint.
Thank you so much. Now I get it. It's like technically possible, but really, really hard, and has some implications about innovation. So thank you so much.
Exactly.
Yeah, I would say that maybe on a different level or more in practice, like we have very robust testing suites. Like on the whole client level, like we have very strong testing tools that are generating tests from specs, right? And those specs will be formally verified. So like the approach there to make it more usable in current time, like it's going to be applied to the tools that we have here.
I mean, quick note on the specs. So if you look historically at Ethereum specs, the very first one was the beacon specs. And this was kind of put in place about 6 years ago or so. And it was the very first time that we had an executable spec. And that was a big milestone in terms of maturity. But we made a lot of mistakes in the way that the specs were set up. It's just very difficult to work with. And then came a second generation of specs for the execution layer. That's with EELS and the Steel team that And here we kind of got a step increase in the usability and the usefulness of these executable specs. And now with the lean specs, which is basically a rewrite of the consensus specs, we're kind of going to the next level yet again. And the way that we're differentiating ourselves is by making the specs AI first. So we have like skills embedded in the specs. We're assuming that the specs are going to be machine read. We have all of the links to the relevant documentation and all the right context, and we make sure to scope things so that we're not polluting the AI context with unnecessary stuff. We just give them the essence of what's going on, and we're basically assuming that the primary consumer of those specs in some sense is AIs. And one of the upshots here is that the barrier to entry to building a lean consensus client is extremely low. And this is the reason that we have over 10 clients now that have joined the development and the dev nets. So we have the OG Beacon clients. There's 5 or 6 of those, and then there's another 12 lean consensus clients. So there's a total of 17 clients, and so we're taking diversity to the next level at the consensus layer. And one of the interesting dynamics is that the teams are very, very different. So in the OG Beacon teams, you're looking at roughly 10 people per team. Whereas in the newer teams, you're looking at roughly 2 people per team. So, the lean meme kind of applies at the social layer as well. We have these lean teams. And, what I predict will happen is that, because most of the heavy lifting will be done by AIs, which will be, the world's best coder, actually many times better than even the world's best coder. There's like no real like technical value add. And so these team leads, if you will be, in addition to being like technical shepherds, they will also be like community leaders, and they will participate in governance, and they'll be, at the mimetic layer in some sense. And so I think the nature of client teams is going to radically shift.
Thanks, Justin. That's very exciting, but interesting specifically for the folks here who are looking into the EPF, the fellowship now, and actually starting to contribute to all kinds of Ethereum infrastructure, whether it's the current clients or the future clients, the lean client repos.
And one thing that I would say here is that one of the key value adds of humans will be friction. Like, we're going to be slow and dumb, and that's going to be valuable. Why is it valuable? Because we basically want Ethereum to be as robust as possible, and we want to enter this maintenance mode and ultimately ossification. And we want to be paranoid and verify everything. And so really the key technical skill that will be valued in the future is, can you sanitize the lean for specs? And can you make sure that the AI is not taking any shortcuts, that really it is proving the theorems that you want to be proved? And you want to be assisting in ways that are ancillary to the core development. So for example, you want to help with documentation, or with marketing, or making sure that there's strong infrastructure to avoid phishing attacks, or whatever, or maybe supply chain attacks, or whatever it is. Your role will change quite dramatically.
Yeah, prompt injection in this case, right? Sort of social engineering for AI. Yeah. Okay. Thank you so much, Justin. Maybe like to elaborate a bit on that, so for people here who've been learning about lean in the past couple of sessions, and have a good overview, like we already saw some specific projects like where they can contribute, but there is so many of these different clients and so on. What are your tips maybe for somebody who wants to find a good place where his sort of input, his work would be valuable when starting to look across the different clients, different parts of infrastructure, or in Lean, in Ethereum?
Yeah. So I guess one good starting point is actually the specs. So because we have so many clients, it's just impossible to coordinate with each one of them individually. If we had a 1 hour call with each one of them, we would be spending all of our week just on calls. And so instead, our strategy has been to have the best possible specs that we could hope for, so that we don't even need to contact them. And this has been a success scenario where a bunch of teams, out of nowhere said, "Hey, we've implemented the specs. This is our new client," and we had never heard of them because they never even bothered contacting us. Even clarifying like what some of the specs were. The specs were just good enough, and I mentioned that the specs need to be AI readable, but we also want them to be maximally human readable. So, go have a look at the specs. Where right now we're adding a lot of unit tests. Thomas has done a fantastic job with kind of first-time issues. So there's a lot of issues that first-time contributors can provide value, and is a good starting point. Once you're familiar with the basics, I would try and find a specific niche that you're especially excited about. So, for example, where we have the peer-to-peer networking layer, where because we're dealing with these much bigger post-quantum signatures, there's probably a lot of changes that need to happen relative to what we have today with libp2p. And actually, there's a new library that was open source just a few days ago called ETH-P2P that Raul from the peer-to-peer networking team has put forward. And so the idea of ETH-P2P is almost the exact opposite of libp2p. libp2p is kind of the Swiss Army knife that can do everything, but it does everything in a mediocre way. And then there's ETH-P2P, which is meant to be kind of tailored and customized for your specific thing. So, right now they're working at the data layer to try and gossip the blobs as efficiently as possible. But the post-quantum signatures is a completely different problem, where you have different topologies and you have different message sizes and things like that. And so one project that could be quite cool is kind of implementing an ETH-P2P module, if you will, for post-quantum signatures. If you're interested in formal verification, there's a lot of fun work to do there. If you're interested in hardcore cryptography, you can dig into Lean VM. If you're interested in DevOps, actually, this has been a bit of a pain point where the DevNets have been quite unstable, to say the least. And part of the reason was that we just allowed anyone to permissionlessly participate in the DevNets. And from now onwards, actually, we had a call today, post-quantum interop call. From now onwards, I think we're going to be much more strict. So, we're going to want integration. We want all of the unit tests to be passed. We want to make sure that your client is stable before it joins the DevNet. So one of the amazing things that we have is not just a fully executable spec in Python for the state transition function. We have the entire client, which is executable in Python. So all the networking is implemented, like the database management, full post rule, everything. So what you can do basically is you can use this Python client for one-on-one interop in a pre-DevNet, if you will, locally. See if that's stable for, let's say, a few days. And if it is stable, then you would go to the public DevNet where you'd be able to test, with all of the other clients. And right now we have one person, Katya, who's working on metrics and trying to identify when things fall over. Basically, she's like one person doing the work of ETH Panda Ops in the context of Lean consensus. And it would be great if people were to help her.
Oh, thank you very much, Justin, for mentioning that, because I think that's a really great example. As Katia was part of the previous EPF cohort, she's been part of the study group as well. You could have mentioned met her here as well. So it's a I think it's a great place to be coming from the fellowship as well. Awesome. Um, yeah. Folks, I will answer some of these questions in the chat, but if you have anything else you wanted to ask, I'm not sure if you want to go back to the execution or just keep asking questions. I think we can go for another till the half past.
Yeah, happy to talk about the execution layer.
Yeah. Because we already talked about it in some of the questions, but before you wanted to give it an overview. So maybe if there is something important we missed.
Yeah. So let me start with the end game. So the end game is that we want the signature aggregation, and instead of going with lean XMSS, which is the XMSS signatures optimized for lean consensus, we're going to go with what we're calling lean Sphinx. So Sphinx is the stateless hash-based signature scheme that NIST has standardized. And it's a very nice scheme. Actually, the I and N in Sphinx stands for incredibly nice. So it's let's see if I can remember. It's stateless, practical, hash-based, incredibly nice, something signature scheme. And basically, what we're doing is that we're taking the NIST standardized scheme and we're replacing the hash function SHA to Poseidon. And here, as I mentioned previously, we have the aggregation that's done on GPUs. So that's why we can afford aggregation, which is 10 times slower because there's 10 times more hashes to verify and 10 times more work to do because you're in the stateless world. But overall, it's all very nice and reuses infrastructure. Now, unfortunately, it's going to take several years. We're aiming for 2029 to deploy this at the execution layer. And so what do we do in the short term? And the good news here is that even today, you can migrate to a whole suite of post-quantum schemes. And this is done in the context of account abstraction. So one of the big enablers that we're working towards is actually frame transactions. Once we have frame transactions, in some sense, that's all we need. So there's one idea which is called ephemeral keys, which I really like. It's very simple. The idea of ephemeral keys is that you have ECDSA pub keys that rotate every time you have a transaction that lands on chain. So the benefit here is that the pub key is only ever exposed to a quantum computer for a small amount of time while it's in the mempool. And very recently, Google Quantum AI had this paper which basically looked at the time it takes to run Shor's algorithm, or even on the fastest quantum platforms that we know of today. And even with very aggressive assumptions, we're looking at several minutes to crack an ECDSA pub key. Let's say 5 minutes. Whereas, in the mempool, the transactions should only stay there for a few seconds, especially in the context of fossil and shorter slots and increased gas limits. So if you rotate your key fast enough, then even though technically speaking, ECDSA is not a post-quantum scheme, when you have ephemeral ECDSA, it becomes post-quantum kind of magically. Now this is a good middle ground for the short and medium term, but in the long term we have something even better with Lean Sphinx and Lean VM. Another kind of short-term solution, which is really cool, is to use hash-based signatures. So you can use Sphinx, but it turns out that you can. There's like other things that you can do. One of them is that you can optimize Sphinx for blockchains. So Sphinx is actually a scheme which limits the number of signatures that you can sign safely. Specifically, what NIST has chosen is 2 to the 64 messages, right? Which is some insane number. It's like 16 billion. So no one in blockchains ever signs 16 billion messages. At most you're signing, 1,000, or if you're a power user or bot or something, you might sign 1 million, but you'll never sign 1 billion messages. And so what you can do is you can retune the parameters of Sphinx Plus to something that's much more reasonable, and you'll get a much smaller footprint. And Nico from the Kohaku team has really investigated the whole design space, and he has this thing called Sphinx Minus, which is kind of a play on words on Sphinx Plus, where he tries to make the signatures as efficiently verifiable as possible. And he even has this new scheme called Jardin, which is even more efficient than Sphinx Minus, and it should be on ETH Research fairly soon. And then there's, if you want, the option to also use lattice-based schemes. So we have on-chain verifiers for Falcon and Dilithium. They will consume a few million gas, but the advantage is that they will be NIST compliant, and there will be, for example, support of Dilithium in hardware wallets like the Ledger Nano S. So if you're extremely conservative, maybe you're regulated, maybe you're part of a security council, whatever, like you might choose to pay the few million gas, which will be a few cents. And if you're only making a transaction every 6 months, then no big deal. The main downside of this solution is that it consumes a lot of call data, and so it wouldn't scale to everyone using it. You would be bottlenecked on call data. So if less than, let's say, 5% of users do this over the next few years, then we're fine. Now, there was this proposal to have precompiles to help to assist basically the verification of lattice-based signatures. And specifically the proposal is to have vector math precompile. So you have a vector of field elements, and you can do addition and multiplication, and that with that you can do FFTs and things like that. And I think this is going to be a useful precompile for all sorts of use cases, including FHE and verifying snarks. But traditionally it was kind of bundled with the post-quantum narrative, and I don't think it has to be bundled with the post-quantum narrative. I think it's just a nice to have, and even without this precompile, so long as we have frame transactions, we're going to be in a really fantastic place in the short and medium term.
Yeah, thank you, Justin. Okay, we have a question, JVN.
Yeah, thank you, Maria. Am I audible?
Yes.
Yeah, okay, thank you. So, yeah, hi, Justin. So, I have been going through this EAP 8141, the frame transaction for quite a bit, and I've been listening to coders. There are a lot of propaganda over there also. But one thing which, when I studied through the EAP, what I find it difficult there or wanted to get your opinion is, the current ECDSA today, the mempool does exactly one cheap operation before deciding whether to invest on any compute. Like that is easy recover. But the concept of 8141, we are failing to get this guarantee. Like we are preventively, potentially doing expensive frame logic, trusting we will get the money after the verify frame actually. So what do you think on it? Yeah, I know there are potential mempool ways to alleviate it, but I just wanted to get your thoughts on that.
Yeah, so account abstraction is one of the things that I have not looked at pretty much at all. I would recommend asking Matt or Felix or Vitalik or various other people. Actually, what you said is kind of news to me. I was under the impression that there was this stateless verification that had a limited amount of gas that it could consume, basically a gas limit that was reasonably small. And if you were to pass this verification check, then you kind of had the guarantee that you would get paid. So yeah, what you said is actually news to me, and that just shows that I'm not an expert in account abstraction. Sorry.
Yeah, sure. Yeah. So yeah, what you're saying is correct. Yeah, but I think we need to do some compute before that actually. So before the verification,
Yeah,
we have some
but
frames about that.
That's fundamental, right? As you said, even in the ECDSA case, you have to do some compute. Namely, you have to check an ECDSA signature, and you actually have to do a little bit more, right? You have to get the account balance and the nonce, and you need to check the nonce and blah blah blah. So this is why the minimum gas for a transaction is 21,000, because there's like 21,000's worth of work to be done, and you're not guaranteed to get paid. And so that's a little bit of a DOS vector. Like traditionally, the way that you would hedge against the DOS vector is, just for example, at the gossip level, if someone sends you garbage transactions, you just disconnect from them. So you kind of ban the IP address or something. And like this kind of soft, Sybil resistance just works fine in practice. And really what we're talking about, as I understand, with frame transactions is that you go from 21,000 gas to something that's larger because you want to express, more complicated things in this pre-verification logic. But no big deal. It should work in practice.
Got it. Yeah, in the case of frame transaction, it's like we are deciding what we should do in place of EC recover. So technically, I can provide a verify function which is predominantly like large and has some like DOS vector there. But I guess I can understand what you are coming at also. So just one more question before jumping into it. So I just wanted to look into this execution layer and on PQ stuff. So is there any place where I can look into it, because I see lean spec and all those are like consensus layer mostly?
Yeah, absolutely. So for the execution layer, we have a call every 2 weeks. It's an ACD breakout call, which is led by Antonio, and anyone can join. They've had something like 4 calls already, so I would encourage you to watch the recordings. There's not that many, and maybe join the next call. I can put you in touch with Antonio. Can share his Telegram handle. He's very responsive, and he can probably share like some of the open problems that we have. I know that Antonio is working relatively closely with ZK Knox, for example. So we gave them a grant, and they are like hardware wallet experts. Like one of the key challenges actually is to make the hardware wallets work. Like we know how to get post-quantum signatures that consume a reasonable amount of gas on the order of 100,000. Certainly less than a million gas, and that should be enough for most users. But the key challenge is the hardware wallets, because they're so slow and so hard to program, and they have limited memory. And for example, Falcon signing is I don't think is been proven to be doable, and Sphinx is like doable, but it's extremely slow. It takes like several minutes to sign a single signature. And so if you're a hardware wallet expert, then we desperately need some clever ideas.
Yeah, I did work on Trezor actually. So like, it signs bit by bit. So it's like extremely time consuming actually when it comes to hardware wallets.
Yeah. If you program Trezors, then please do get in touch with Antonio and the ZK Knox team.
Sure. Yeah. Thank you, Justin. Thank you for replying. Yeah.
Very well. I will get back to that later, but Lee has a question.
Okay, yeah, thanks a lot. I feel like the hardware issue is not only our issue, right? Considering like there are so many hardware verification
Yes.
tools for banks, I assume they should be panic in front of us.
Yeah, that's a good point. Now, the thing is that the NIST standards are very, very fresh. Actually, the Falcon signature scheme hasn't even been like fully finally standardized. We have a draft. So the only two that are standardized currently is the Lithium and Sphinx Plus. And even for Sphinx Plus, there's like a new draft for new parameters that came out just a couple of days ago. So even the standards, potentially will grow over time. I mean, I think we should basically expect the next generation of hardware wallets to provide like some amounts of support, but these hardware wallets only get refreshed infrequently. I mean, as I understand, it's possible that the next Ledger wallet will come in 2027 or 2028. I don't know exactly, but because of the release cycles being so long, we're in an awkward situation where if you wait till 2029, you'll have the amazing endgame solution with aggregation, and everything will be super cheap and super scalable. But yeah, do we really want to invest a lot of effort, for a 2028 solution? I don't know. This is not me to make the call. My personal guess is that most of the rest of the world will basically adopt lattice-based solutions. That's what NIST encourages, and it is very much probably one of the best schemes that you can hope for if you're verifying signatures on an individual basis. But for blockchain specifically, where we have this batch setting, and when we're absolutely paranoid about cryptography and we want our cryptography to live on for decades and centuries, hash-based really is the best solution. And so it's possible, we're going to have to come up with our own solutions for hash-based, because the hardware manufacturers won't be incentivized. Well, they'll be primarily incentivized to build lattice solutions. One piece of good news is that I believe the next generation of the ledger will come with Keccak acceleration. So we'll be able to have faster Sphinx Plus signatures, for example, at least with Keccak. But yeah, I don't have a good answer to this.
Yeah, don't worry. It's already a good explanation, and I feel like Sphinx Minus is such a good idea, because we noticed something within similar idea before in last cohort of the EPF, like MSM for the KZG commitment. Ideally, could be pretty slow, but since in our setting, in DA setting, we only have like 4,000 points, and also we already know all the secrets we are going to use, all these like group values we are going to use to encode. Actually, you can cache a lot of things to accelerate the performance theoretically. So,
Right.
Yeah, so in our setting, we can do quite a lot of optimization, I feel.
I agree. Yes. So there's all sorts of caching optimizations that you can do with Sphinx. Basically, you have what's called a hypertree, which is a tree of trees, and you can cache various layers of the tree. And there's like this blog post that someone in Bitcoin land wrote with like 10 different optimizations to Sphinx Plus, and you could see kind of performance incrementally improving with every optimization. So you can go pretty crazy on optimizations. And my hope is that we eventually get signing on hardware wallets, which is on the order of 1 second, which is perfectly fine for most settings.
Very well. We have a couple minutes left, folks. If you have one more question, please go ahead. Okay, Andres had a couple of them, but I guess can take the last one. Go for it.
Thank you. So yeah, it's more like a follow-up question about where can we contribute to Lean consensus. I think a good part of that question was answered thanks to the GBN question. But yeah, it's more like what are the repositories or what are the efforts being applied in the terms of developing like the guest program or the CKVM that we are going to use or the pooler that we are going to deploy, and yeah, are going to be like the light clients that are going to verify the proofs. So yeah, where is that code and where we can like actually start contributing to that?
Yeah. So I guess the meta answer that I would give is to talk to Thomas Corragé. So he's the post-quantum team lead, but he's also the guy who's writing most of the specs and who's shepherding um, a lot of that. And he also implemented the Python client. So he's trying to really make this a collaborative effort. So he has these like good first issues that you can work on that I mentioned. And he's very, very responsive. Like you send him a message on Telegram and you'll get an answer within a few hours, if not immediately. Yeah, I mean, there's in some sense there's a lot to do, but in another sense, things are reasonably under control. So when I started the Beamchain project a year and a half ago, I would never have dreamt that we would be at the place where we are today. We're just moving at warp speed. It's incredible that we have basically specs, we have 10 implementations, we have a DevNet, we have this cryptographic library, which is ultra efficient. We've done all the research, like we're in such an incredible shape. I think now what we need is people who have a productionization mindset, right? Like how do we go from DevNets to testnets and eventually mainnet? We need reliability engineers, security engineers, DevOps people. I mean, when you go back to the beacon chain, when we wrote the beacon specs, we were in a very primitive position where we didn't have any of the productionization teams. So the Panda Ops team didn't exist. It was specifically set up for the beam chain. Same thing for the security team. That's a team that was basically spun up just a few months before we deployed the beacon chain. And we have the prototyping team and like all of these productionization teams. And one of the things that we're seeing right now is that none of the three teams that I mentioned, literally 0 people right now are actively working on Lean consensus. So 0 people from eFounder Ops, 0 people from Steel, 0 people from prototyping. And so there's a lot of low-hanging fruit. And like you could be, if you want, like the guy who's this, the Lean security expert, or the guy who's the Lean testing expert, or DevOps expert. And I mentioned Katya, who's who I guess is a great story because she was a fellow, and I'm she's a little overwhelmed right now with being alone, having to work with 10 different clients that are unstable, and I think giving her a knock could be appreciated.
Great, that's great to know. Thank you so much.
Thank you very much, Justin. Indeed, I think this is a great place to finish the session, also because that's also where we continue with the study group and with the EPF. Actually, we will be in coming weeks gathering more specific inputs from all the protocol teams, including Lean teams, on where they need help with. So for the next steps, like in next month, you will see actually some ideas for fellowship projects coming from these teams. We had like Reem participate before the the one in Zine. Oh my God, there's so many of them. So we will have those opportunities also coming for you. You can also check the good first issues on GitHub always, and I shared a couple of repos right here. So uh, that would be the next steps for you all. But yeah, thank you so much, Justin. Let me start with that. It was really great to have you here. Very insightful. I believe we all learned a lot, and it's just very inspiring. It's just always so motivating to hear you like this technical optimism and just the strong vision for the future is it's very exciting to have to rely on. So thank you so much for being here today.
Absolutely. And feel free to reach out anytime. I'm Justin Drake, all lowercase on Telegram.
Awesome. Oh, that's amazing. Thank you so much, Justin. Very well. And thank you so much, everyone who attended. Thank you so much that around 40 people here today. Thank you so much for being here for the very last session of the study group, but especially for all of those who made it through the 2 months period of learning and last couple of weeks of these calls to always be here and learn with us. I see the names here that I've been seeing for 2 months, so it's incredible that you made it. And now at the end, one huge thank you. We will have some participation badges sort of for you that you can receive to your email that you use to register on the study EPF wiki. We will post some information about it later in Discord. You can reach out if you have questions. Also, I would like to invite you for ETH Prague, Ethereum conference in Prague in 3 weeks from now. If you can make it there, we have a free ticket for you. So if anyone is interested in ETH Prague tickets, you can also reach out. We will have a post about it on Discord. And finally, I would like to invite you to apply for the fellowship. So the EPF program that we talked about with more opportunities to contribute, work directly with the teams around all the ETH R&D, including lean, execution, consensus, other research, testing, and DevOps as well. If you are interested in continuing your journey as a contributor, we also have the application opening now in a first version for you from the study group. Josh, if you have the link, please share that here, and please don't really post it as of now. This is like a first release before the official announcement. The deadline is in a couple of weeks. You have plenty of time. This is very early just for you who made it through the study group, because it's been really great having a community that learns together and is able to support each other and just progress so much over the past 2 months. We went from like, what is a client, what is a consensus layer, what is the execution even doing, to like the wild future of lean and everything that's waiting for us. And I think the amazing part is that you can contribute to it, you can become part of the future. So please check out the fellowship and all the repositories, opportunities to contribute. And again, thank you so much, Justin, for being here to wrap up the study group. I think it's been really great and especially inspiring ending to conclude this journey. Yeah, thank you so much, everyone.
Thanks, guys.
Yeah, thank you so much. Awesome.